All right, so now I'm going to introduce to you what we call a titration. A titration is kind of a little experiment, a little reaction that you perform in which you combine two reactants and you have an understanding of how they're going to combine, which we call a chemical equation. You have a chemical equation to know the ratio in which they combine, and you know what the products are going to be. And one of your reactants you know the concentration of, while the other one you don't know, and you're going to use your known to identify the concentration of the unknown. All right, that is kind of a simple definition of a chemical reaction, a titration. You do need, generally, people think about titrations, they think about, I don't know, have you ever heard of titrations before?
Yeah, acid-base titration, is that what you mean?
Yeah, that's right. Most people think about acid-base combinations in a titration, and that's fine. That's where we cut our teeth and learn.
I don't have any teeth.
Oh, sorry about that. Well, are you growing them?
Yeah, they're getting bigger, but it's really slow. I've got some sort of genetic thing going on.
Okay, that's fine. You can, you don't have to share with me. You might want to talk to your genetics advisor, though, or in your class. Are you taking genetics?
Next semester.
Okay. So, in a titration, we have what's called the titrant and the titrate, and we have an endpoint in the chemical reaction. And this is a required component because you need somehow to tell you that the reaction has come to completion. Okay? So, usually this is performed with a burette, and in your burette you have one of your reactants, and then you have a beaker, and in that beaker you have another reactant. So this is an example of an acid base. I put my base here and my acid there. I could have switched it around, it doesn't matter. And I have a dye that tells me when the pH changes. Have you ever seen dyes that change color at different pH?
Yeah.
Yeah, you can make them at home, right? Maybe, have you ever washed dishes?
Yeah, why?
Well, if you wash dishes, sometimes you can see the color of your food changing as you dilute the solution. And that's because the pH is changing of those chemicals in the food. So blueberries is a good example, or red cabbage changes color as you dilute it. Okay, the change in color for acid-base titration is how we identify the endpoint. But in any titration, there's lots of ways to identify the endpoint, but you need to find a way to identify what the endpoint is when it occurs. Okay, and then afterwards, you can just use the molarity of the initial concentration. You can use the magic of the equation, which is the stoichiometry, the mole-to-mole ratio. And then you can use the volume that you started with to know how many moles were in what liter of that given solution. So let's give you an example here. So this is a titration. 25 milliliters of HCl was titrated with 75 milliliters of my 1.3 molar calcium hydroxide. And from this, I can calculate what the concentration of that HCl was. Okay? We have a known, we have an unknown. We know how these will react chemically because we have some experience. And apparently we had a way to know when the endpoint was. So we found out what the volume necessary was, and we can calculate the concentration of the HCl. Let's write our chemical reaction really quick. Okay, so what are our reactants?
Is that just the HCl and the calcium hydroxide?
That's right. Here we have HCl combining with our calcium hydroxide. Okay, what are our products?
Water and calcium chloride.
Water and calcium chloride. Now I'm going to let you tell me the chemical equation for the calcium chloride, but anytime you write a chemical equation, you have to be mindful and think about the combination.
Oh yeah, so must be 2 chlorides. That's why you stopped me.
That's right. CaCl2. Very good. And again, we use our periodic table always to, if we're in doubt, for identifying what the charge would be on whatever atoms we have, right? Or our polyatomic ion chart to answer questions as well. Okay, are we balanced, this equation?
No, we need 2 HCl and we get 2 waters.
Very good. Balanced now?
Yeah, I think so.
Okay, very good. And it's important to be balanced, or was that not a big deal?
No, you need to because you can't get the power of the equation in the land of the moles unless you balance it.
That's right. Very good. So now we can start with our equal sign. What goes to the right of our equal sign?
You want the concentration of HCl.
Okay. So what are my units?
Molarity.
Okay. But I'm not going to write big M, am I?
Oh, no, okay. Just write moles of HCl per liter of solution.
Very good. Why do I put it out individually like that?
Because it's more clear what you're after.
Very good. So now what can I start with?
I don't know.
Well, the moles of HCl, it relates to what?
Oh, the moles of calcium hydroxide?
Yeah, we have that, right?
Okay, so start with your moles of calcium hydroxide.
Okay, did they give me moles of calcium hydroxide?
Not directly, but they give us the molarity, 1.3 molar.
Okay, very good. 1.3 moles of calcium hydroxide for every liter of that calcium hydroxide solution. Right?
Yeah.
Okay, good. Now I'm in liters of calcium hydroxide, moles of calcium hydroxide on top. Can I work with that? What can I do?
You can convert the moles to HCl.
Very good. Moles of calcium hydroxide to moles of HCl. What's the ratio?
2 to 1.
Good. We found that out earlier. That's our stoichiometry here, right? Good. Now I've gotten rid of my moles of calcium hydroxide. I'm in moles of HCl like I like. Almost there.
Yeah, and you got volume of calcium chloride up there. 75 mils.
Okay, 75. Can I convert it?
Yeah, just convert it to liters.
0.075 liters of my calcium hydroxide solution. Okay, am I done?
Yep.
So the liters cast out here, is that what I wanted?
Yep. Oh, wait. Must be something else because you're not saying done. Oh, we need liters of the HCl solution on the bottom.
That's right. We need liters of the HCl solution down here. We got rid of our liters of calcium hydroxide, but we need our liters down there.
Well, they did tell us 25 milliliters of the HCl, so that's 0.025 liters.
Very good. So I can put that in there. That's liters of the HCl.
Now, are you sure it's okay not to have anything above or below those volumes?
Yeah, that's all right. All we need to do is get the right units over here. So I don't need to have anything in those missing spaces. Not everything is expressed in terms of like moles per liter, or this is the molar ratio, right? If we just need to get rid of these moles of material, or these liters of material, we can do that with, these liters of material. We can just do that by multiplying by liters of the material that we used. All right, very good. So our answer should be 1.3 times 2 times 0.75 divided by 0.025. Okay, so 7.8 molar HCl. So we did a titration reaction where we identified the concentration of the HCl from the results of a titration. Okay, here's another one. Sample of metal ore is reacted according to the following reaction. If 25 mils of 2.3 molar HCl are used, what mass of iron was in the ore?
What's ore?
That's a good question. Ore is just dirt that's rich in a given element. So this is dirt that has a lot of iron in it. So we call it iron ore.
They gave us a chemical reaction.
Yeah, that's nice. It is a net ionic equation though, right?
Yeah.
So it might look a little confusing.
Yeah. I'm going to need help with that.
All right. 25 milliliters of 2.3 molar are used, and we want what to the right of the equal sign?
Mass of iron. Grams of iron.
Very good. So we're looking for mass of iron, grams of iron to the right of our equal sign. Excellent. What am I going to start with?
You know that what is the chemical reaction telling us?
Yeah, what is that telling us exactly? It's saying iron combines with two H pluses. Where do we get the H pluses?
I don't know.
Well, H plus, where can you get the H plus ion?
Oh, from the acid?
That's right. And did we use acid?
Oh, HCl. So the HCl gives us the moles of H plus, and the moles of H plus gives us the moles of iron.
Very good. Very good. Now that was kind of difficult to see, maybe.
Well, you help me, but I think I can see it next time.
Okay. I'd like to approach this one just a little bit differently to show you a different method. I think most of the folks at home probably know where to go from here. And if you do, try to finish it up before I show you what to do. Always try to finish up problems before I show you what to do. But I'm going to approach it a little bit different. I know I want grams of iron. All right, I know I want grams of iron in this one. I might be confused about anything else, but I know I want grams of iron, and I know that I could set this up. That was brain cell free. I got it for free, right?
Good, because my brain cells are running low.
That's right. That's right. You got to use them wisely. But if I work backwards here and go grams of iron, I can go to moles of iron. Now, I knew I wanted to go to moles of iron. Maybe I didn't know that intuitively, but there's a molar ratio of iron here in this chemical equation. So then I can go from moles of iron to what?
Moles of H plus ion.
Yeah, I can see I can go to moles of H plus ion. What is the ratio there?
The stoichiometry is 1 mole of iron for every 2 mole of H plus.
Very good. So now, moles of H plus ion, and I should be able to work backwards at least that much with a couple of brain cells, but not a whole lot, right? So I've started with grams of iron this way and got rid of grams, got grams of iron from my moles of iron. And then I got from my moles of hydrogen, where am I going to go?
Moles of HCl.
That's right, moles of HCl. Okay, and that's a 1-to-1 ratio, 1 H plus for every 1 of HCl. And then I can go from, I'll put that in there, 1-to-1, moles of HCl to where?
Well, they told us moles of HCl, didn't they? They told us 2.3 molar, which is moles of HCl per liter of the HCl solution.
Very good. So that is our 2.3 moles for every 1 liter of our HCl solution. Excellent. Now all I need to get rid of is my liters of HCl. Can you see that? I got rid of my mole. I got moles of HCl there. I'm in grams of HCl iron like I want. Now I just got to get rid of this liters of HCl, and that's my 0.025.
The 25 mils?
That's right, of the HCl solution. So 0.025 times 2.3 divided by 2, and that, what do I need here?
Oh, that's grams of iron for every mole of iron. That's just the periodic table. Do you have that?
Yeah, so that is iron 55.847. 55.847 grams for every mole.
Okay, good.
Excellent job. So 1.6 grams of our iron solution. So maybe some of you knew how to start and work forward, but this is another tool that you have working backwards, just by kind of, again, looking around, seeing what you know you have to end up with and what kinds of information they give you. Okay, good work.